Okay, so hello all. I'll start in about a minute. Let others also join. And so my name is Varnit. Welcome to the week 6 tutorial lecture of the course CFD using finite volume method. I hope everyone has watched the lecture videos by the professor on the portal up till week 6 and have completed their assignments as well. Okay. So in the previous tutorial, we discussed about TDMA, okay, and also we discussed about a lot of other things as well, about the source term linearization and all that. And today we will be starting with a 2D problem for TDMA because we discussed a 1D problem of TDMA already. I hope everyone will be comfortable because we have already learned 1D and we have understood about the sweeping and traverse directions. Okay. All right. I hope I'm visible, I guess. Not sure. Okay. Yeah. Yes. I guess it's working now. Okay. All right. Mhm. Okay, someone will join. Okay. Yeah. So let's start with the 2D problem of TDMA. So if I have the boundary, let me make. Okay. Um, all right. These are the 4 cells. And this is 1, this is 2, this is 3, and this is 4. And the boundary conditions are TA is equal to 100 degrees Celsius and T at B is equal to 200 degrees Celsius and T at C is equal to 300 degrees Celsius and T at D is given to be 400 degrees Celsius. Okay. Also, there is no source term. We are assuming source is 0. The conductivity of gamma can be said to be 1 watt per meter Kelvin. Okay. And the spacing is like del x as well as del y is 1 meters. So using the line by line TDM technique for 2D, because we have discussed this kind of technique. So we'll traverse in the y direction and uh, sweep in the x direction. Okay. So that means we have this much as 0.5. This is 0.5. Okay. Now let's come to cell 1. Let's come to cell 1. And you can tell me at any point of time if you have any doubts, because it's a live interactive section. Right? So for cell 1, there is a east, a west, a north, a south. Okay, it's a two-dimensional. So we are applying TDMA here. Okay. And we are assuming the values T3 star, T3 star, and T4 star. Okay. And we want to keep the values are T1 and T2. Already we have seen the algorithm for this. So A east will be is gamma delta y by gamma east delta y by del xc. Okay. So gamma delta y. So east is for the cell 1. East is this, west is this, north is this, and south is this. All right. So gamma del y, because gamma EAE by del x. So A east will be how much? This is del y. And it's two-dimensional. So 1 unit in the z direction. And this is del x. Okay. So gamma into del y by del xc. So what is del xc? Between east and point under consideration, that is 1, the node 1. So that is gamma is 1, del y is 1, del x is how much? 1. It will be 1. Similarly, A north, if I want, or A west, I want, first of all. So gamma west, del y by, but this time there is no west node, so we'll take the boundary node by 2. So that is 1 into 1 over 1 into 2. That is 2. Now coming to the north point, the north will be gamma n. Area will be del x into 1 unit into del y north. It has a north node, north, it's a node that is 0.2 there. So 1 into 1 over 1, that is 1. And A south will be gamma s del x. Again, there is no node for the south, so it will be just the boundary. 2 into 1 by 1, that is. So what we can say, our equation is AP, IP, okay, or APTP, you have temperature, is summation of neighboring nodes, TNB, TNB, plus some source. But source is 0 here, so sums are 0. Okay. Or plus another values as well. So AP is summation of all the neighboring nodes of it is 2 plus 1 plus 2 also 1. That is 6. 6 T1 is equal to T2 is unknown and T4 is unknown. Here, if you observe here, the T2 is unknown and T4 is unknown, whereas left and the south, west and the south nodes are directly the boundary nodes. So that is A west, A north first, let me write. So with north, what was the coefficient? 1. Okay, so 1 into T2. And for east, what is the point? It's the 0.4, and east has also 1. A east into T4. Whereas for west, AW, it has 2 as a coefficient into what is the temperature? 100 degrees Celsius. 2 into 100. Plus, again, the coefficient for south is 2. A south, if you observe here. And the temperature, the boundary is given to be 300 degrees Celsius. So that is 6 T1 is equal to T2 plus T4 plus 200 plus 600, 800. This is your equation for node 1. Similarly, you can write the equation for node 2, 3, 4. Okay. If you see for node 2 is unknown. So what are the neighboring cells that are unknown? 1 and 3. Okay. So 1 and 3 has 1 T1 plus 1 T3 plus 1000. Multiply with the coefficient. Node 3 has 2 and 4 as the neighboring nodes. So T2 plus T4 plus add remaining temperatures, the coefficients, it will be 1200. And 6 T4, 4 has 1 as well as 3. So 1 T1 plus 3 plus. These are the 4 equations you have, right? Now you have discretized your domain, you have solved the equations and got the algebraic. You have got the algebraic equation. Now you will solve the equations. Okay, using TDMSK. So, as you know, all these 4 equations. Now you have assumed the value of T3 star is equal to T4 star is equal to 100 degrees Celsius. It should be a bounded value. Okay, so from minimum to maximum, what is the minimum value in the boundary? It is 100 and maximum is 400. So let us assume it is 100 itself. 100 degrees Celsius. Now, if you use this value for the first, because we are doing TDMA in Y direction and sweep in X direction. All right. So you know what was the algorithm? T1 is equal to B1 over A1. If you watch the pictures, you'll find that. So T1 is equal to B1 over A1 and Q1 is equal to B1 over A. So if you see for the node 1, the equation 1, what is B? B is 1. B is 1. Sorry, not this equation. Equation number 1, this one. So B is 1 here. Okay, and A is 6. So 1 over 6. And Q1 is equal to Q1 is D1 over A1. So D1 is how much? 100 plus 800 over A1 is again 6. 100 plus 800. Because we have assumed that T4 star here is 100 degrees Celsius plus 800 will also be there. That completely gives you D1. Okay. 100 plus 800 by 6, 900 by 6, that is 150 is your Q. You got P1 as well as Q1. Now, P2. P2 itself is B2 over A2 minus C2 P1. We know that Bn equal to 0 for trivial solutions. And 2 is the Bn because we have just 1, 2, 3, and 4. So while traversing from 1 to 2 to 3 up to n, here our n is itself 2 because we have just 1 and 2 in the y direction. So it is the Bn. So B2 will always be 0 for trivial solutions. We have seen this thing. And Q2 is D2 plus D2Q1 over A2 minus C2P1. So if you observe this equation, because you are dealing with 2, note 2 right now. So T3 is 100 plus 1000. This is D2. So that is 1100. 1100. How much is C2? C2 is 1. And Q1 we have calculated as 150 over A2. A2 is 6 minus 1. C2 is 1. And T1 we have computed as 1 over 6. If you solve it, you will get 214. Q2 as 214. Now we know that T2 is equal to Tn is equal to Qn because 2 is the nth point while we are traveling. So we know that Tn is equal to Qn, so T2 will be equal to Q2 itself. So that is 214 degrees Celsius. Now we know that T1 is equal to T1 Ti plus 1 plus Q1. So P1 T2 plus Q1. So P1 is 1. P1 was how much? We have computed 1 over 6. And T2 we have got 214 plus Q1 we have solved 150. So that will come out to be 186 degrees Celsius. Are these T1 and T2 186 and 214 bounded in a bounded region? Yes. 186 T1 is 186 and 214 T2. So they are under the boundedness between 100 to 400. All right. So I guess similarly, you got the value. Now you sweep in the other direction. Take these guess values, calculate T3, T4. Taking these guess values of T3, taking these as the values, you will solve for T3, T4. You already have T1, T2. Okay? I guess this can be done. Any doubts? Yes, Priya is there. Priya, do you have any doubts? You can unmute and ask. I hope you have watched the lecture. Then only you can ask. If you have any doubts, can you unmute yourself? Okay. No doubt. Okay. All right. We have mentioned in the chat. Okay. Now, let's understand under and over relaxations. Let's come to that. The topic of under over relaxation. So in iterative schemes, sometimes we want to accelerate or slow down the process, the iteration process. So we want to change the dependent variables by making them either over relaxed or under relaxed. Okay. So if you have a delta phi, which is phi p minus phi p star. So if you want to reduce the rate of iteration, you will multiply with a factor that is less than 1, between 0 to 1. If you want to increase, you will multiply with a factor that is greater than 1. Okay. When it is less than 1, you say that it is under relaxed. But if it is greater than 1, That means you can say it as a over-relaxed system. Okay. Let me write it here. In iterative schemes, sometimes we want to accelerate or slow down. Suppose you have delta phi p, that is phi p minus phi p star. If you multiply here with some factor, then you will get, this is nothing but a change of the dependent variable. Okay. Either you can over relax or under relax here. Over or under relax by multiplying with a factor. And it was by chance this happened, and then a lot of theories came about the under and over relaxation schemes. And in nonlinear problems, to control the change of phi from iteration to iterations, we do some like Gauss-Seidel successive over relaxations, okay, or under relaxations as well. So nonlinear problems, control the change phi from iteration to iteration. So there's one scheme that is Gauss-Seidel successive over relaxation. That is nothing but GS SOA. And for nonlinear problems, there can be under relaxation as well. Under relaxation. So suppose you multiply, because you have the change of phi, if you multiply with a factor 0.6 less than 1, which is nothing but alpha, which is your relaxation coefficient. Okay. So this is by experience, you understand. There are some techniques as well to understand how you will select the value of the relaxation coefficients. Okay. So if our equation is like this, as we have seen this equation multiple times, that is APTP is nothing but summation of neighboring roads A and B, T and B plus the B. Okay. So if I divide with the AP, so what will I get? NB, ANB, TNB over AP plus, let me write like this, plus B over AP. Okay. And we know that TP star is nothing but previous iterative values. We just did above question. Okay. So if I add TP and subtract TP on the right hand side, okay, TP is equal to TP star plus one is trying to find TP star. Hello. Okay. TP is equal
10-15 minutes के बाद.
Yes, Paul. Do you have any doubts? Okay. So TP is equal to TP star if I'm adding TP star and subtracting TP star from both the sides. That is nothing but summation of A and B neighboring nodes, P and B plus B over AP, and I'm subtracting TP star as well. The equation remains same, balanced. Now, what is happening? Change in TP in the current iteration, if you observe, this is nothing but, if I bracket here, this is nothing but TP minus TP star, because your this term was TP only. If you see, this term was TP only, right? TP, not TP, TP only. So that is TP minus TP star. So that means if I multiply this term TP minus TP star with some coefficient alpha, that means I can change my iterator's process to be faster or slower as per my need. That is plus multiply with some coefficient alpha into TP minus TP star. Okay? TP minus TP star. Or instead of TP minus TP star, I can write it as a whole equation. TP is equal to TP star plus alpha times this alpha times summation of neighboring nodes A and B, I and B, no sorry, T and B plus B over AP and minus TP star. Right? Now, if I again divide by multiply with AP and divide by alpha on both sides, so what it will be? TP into AP by alpha is equal to TP star into AP by alpha plus summation of neighboring nodes A and B, P and B plus B minus AP TP star. All right. I've multiplied with AP on both sides and divided by alpha. This is your final equation where you can say AP over alpha into TP is equal to summation of NB, ANB, TNB plus B plus AP by alpha into 1 minus alpha TP star. Just I've grouped these two terms, this term and this term together as 1 minus alpha. So this is your relaxed equation now. This is your relaxed equation. This is your relaxed. And when the solution will converge, then TP it will be equal to TP star. So that convergence, the last iterative value and the current value should be equal. So at convergence, your TP will be equal to TP star. So again, you will get the same equation which you wrote, AP by alpha TP. This equation, relaxed equation only I'm writing. Summation of A and B, P and B plus B. I'm expanding the term plus AP by alpha TP star will be equal to TP here. This TP star will become TP because of convergence minus alpha minus AP. Alpha by alpha is 1 into TP. So if you observe, this term and this term get cancelled out and you have the same equation. There is no change. Again, you have APTP is equal to the first equation which was made, this equation. So that means by giving this equation, that means by giving the under relaxation or over relaxation does not just slow down or fasten your process. Okay? But at final convergence, the result will be coming out to be same. Okay, so under relaxation only changes the path to the solution. Okay, that how fast or slow you want to go, and recover the original linear system of equation at convergence. Recover the original linear system of equations at convergence. And any relaxation scheme should satisfy this condition at convergence. Otherwise, your solution will diverge and will not give the correct results. And any relaxation scheme should satisfy this condition. All right. And if alpha value is between 0 to 1, we say that if alpha is between 0 to 1, what can we say? It is a under relaxed system. And if alpha is greater than 1, we say that it is over relaxed. Okay. So as to improve the diagonal dominance. Okay. And alpha value, as I've told, depends on your experience that how you got that value. And yeah. So as to improve the diagonal dominance. So you can take alpha value very high values as well, but again you have to see your solution is getting diverged, shouldn't get diverged. It should always converge. So it cannot be like you can take 100 as alpha for over relaxation and you want to simulate your process in such a way that the simulation should end in within fraction of seconds. I'll put alpha as very high. No, that's not right. We'll get a diverse solution. We should maintain like 1.2, 1.3. But it's all depends on the experience and expertise. Then you will be into this. And there are recent research is happening which are telling about like schedule relaxation, Jacobi minimization problem is there to deal with that. So yeah. I hope any doubts still here? We have done the two-dimensional TDMA problem. We have understood about the under relaxed and over relaxed system. Okay. No doubt. Uh, Paul, Paul Naveen, are you there? Hello, Paul. Can you unmute yourself? Or if you are unable to do, can you just type it in chat box if you have any doubts, no doubts? And Priya as well. Do you have any doubts? No doubts? Okay. Okay. No doubts, Sherry. Okay. Great. All right. So I hope you guys have done your assignment problem as well. Now we will come to steady diffusion in other coordinate systems like polar coordinates, a cylindrical coordinate system, and axisymmetric coordinate system. So we have dealt with the Cartesian coordinates. Now we'll deal with the polar with axisymmetric coordinates. Steady diffusion in other coordinate systems. So far we were dealing with Cartesian coordinates. Now we will deal with polar coordinates or cylindrical coordinates. And third, we will deal with axisymmetric coordinates. All right. Now let's come to polar coordinate system. Which is comprising of nothing but R theta system. Okay. R theta system. And we'll first deal with the two-dimensional problem only. Will not include third dimension that is Z here. So both now my grid will look like something like this. I guess I've made some. Okay, I guess this will be fine. Okay. All right. Suppose my cell under consideration is the cell. This is my cell of consideration. The point. So this will be the north face, east face, south face, and west face. Suppose I take an axis passing through the center of this cell, which has a radius of RP, has a radius of nothing but. Please understand this very carefully. The frame of polar coordinate system, so that when I'll be discretizing the equation, this will be very needful for you guys. Okay, and the width of this is how much? Use some other color. Is nothing but del r. Del r. This angle is complete angle is theta. This complete angle is del theta. Okay. So we can say that if a line is also passing from here in both r and theta directions, so this much will be del theta west, and this will be del theta east. Okay, del theta east, del theta west, del theta east. The coordinate system is look like this. So this is your theta direction. This is your r direction. R is unit vector is ER, and for it this will be E theta hat. Okay. Then this was your south face. This was your south face. So radius for south face will be RS, and radius for north face will be extended till here. R north. Okay. R north, RP, RS, the radius. So we have seen del theta W, del theta east. Similarly for north and south, this will be, let me choose some other color. So del Rn, this much is del Rn, and this much is del Rx. Okay. Del Rn, del Rs, del theta west, del theta east, and all the radiuses, and del R is the width of a unit cell. I hope till here it is very clear. If you have any doubt, please ask, because we'll start with the discretization of this. Any point you are finding, just observe for a minute this whole, and you can draw it in your notebook as well with your hands, so that will be more helpful. I'll give you a minute or two to observe it carefully and draw it as well. I hope everyone has drawn. All, Priya, you have drawn, understood. All, what do you do? Can you unmute yourself and tell me? Like it should be an interactive session. That will be helpful. Okay, no problem. Okay. Can I proceed further? Or you want more of minutes? Proceed. Okay. What about Paul? You want 4 minutes? You can unmute yourself, guys. You can unmute yourself and talk. No issues. And what do you do, Paul?
Hi, sir. Good evening.
Yeah, hi.
Yeah, I'm a assistant professor,
Okay.
teaching and teaching in a university in for the subject petroleum engineering.
In Dehradun.
No, I'm currently located in Gandhinagar.
Okay, I thought Dehradun Petroleum Engineering you're talking about.
Yeah, in
Okay.
Gandhinagar, Pandit Deendayal Energy University.
I have heard about this. Yes, yes, yes.
Yeah.
Okay. Great, great, great. All right. So what
So
motivated you to join this course?
we do deal with lots of flow mechanisms. So I felt like we were all most of the time confined with the transport mechanisms, especially with gas and oil. Since we
Okay.
deal in petroleum engineering, I felt
Yeah.
like let me understand some more insights because reading a book it's getting more difficult. Let me
Hmm.
follow any one of the course of this kind so that I can like, understand more and more better.
So you are regular to watching the videos of Professor? Lecture videos? Uh,
Uh, yeah, I sometimes I couldn't make it, so I watched the YouTube videos again. But this kind of practicals, yeah, now just now I'm on the way when the lecture was going on, so I couldn't
yeah.
completely follow it, but yeah, I was able to give the message here and then.
Yeah.
Yeah.
But
So
you have understood about the Cartesian coordinates from previous lecture videos. So
Right,
now
right.
we
Yeah,
are
yeah.
dealing with the
Yes, yes. I do
polar
have.
coordinates.
Yes,
Mhm.
I did understand. And I really appreciate the way the teaching is going on, and you're
Yeah.
making sure that the part of tutorials are also covered. So I really
Yes.
appreciate
Yes.
this.
Thank you. Thank you.
Thank you.
Okay. All right. So let's start further. Okay. So coming to the polar coordinate, we have defined our geometry. How does it look like? Okay. Now we'll start discretizing it. So let me write here. Start writing. So our equation for 2D diffusion is nothing but, we have seen it hundreds of times. Del of K del T plus ST equal to 0. Steady diffusion. Steady diffusion case. Okay. Now, if first of all we are dealing with the control finite volume technique, so we will integrate first of all over the control volume. So del of K T dV plus it's over a control volume. Again, this also control volume. So T dV equal to 0. Now we will apply the Gauss divergence. Gauss is until here the same process as that of Cartesian coordinates. So del of any function f dv is f dot n cap. Yes, f here is k del t unit vector that is dot t. This is a vector over control surface this time. And here it will be control volume only, st dv equal to 0. So this can be written as summation of the neighboring nodes, east, west, north, south, all the faces, east, west, north, and south. So k del t of all the faces dot as. Okay, plus we assume the averaging over the SOSA, so st del v equal to 0. St del v equal to 0. Now, what is del v? So del v, if we have a cell P, if you observe, this was your cell P. This is the length of this will be how much? R del theta, R of south. First it is R of south or R of P. Okay. Because I am dealing with at the point P, so I'll take the radius of this R of P. R of P del theta. This is your arc length. And this is how much? Del of R. Del of R into del of R. So RP del theta del R. So your del V is nothing because, and in Z direction it will be 1 unit. RP del theta del R. This is your volume. What is your grad operator in cylindrical coordinates or polar coordinates? It's nothing but unit vector in the radial direction, dou by dou R, plus unit vector in the theta direction upon 1 by R, dou by dou theta. So how can I write K at T? It can be written as K unit vector dou by dou R of T at each face plus T theta 1 by R dou by dou theta. Okay. Should not write here anything east face right now. We are just saying it's a, or if I say it is a east face, then I can write this for east and this will be R of east as well. Okay. What will be A of east? And okay, make sure one thing. This was your east face. This was your west face. So this is your RP. Till here it was RP. So if you see, RP is equal to RW is equal to R east. All have the same radius. All have the same radius. RP, RW, RE. Okay. So either I write RE, either I write RP, doesn't matter. Now what will be A area of east? Because this is the term now. K grad T dot area of that face. K grad T we have seen for the east face. Similarly, area of east face will be how much? It will be for the east face. If you observe, this is your east face. This is your east face. What will be the area of this? Del R into del R into 1 into E theta. Because it's pointing in the E theta direction, theta direction. This is your theta direction. We have already defined our system. This is your theta direction. Okay. Del R into the unit vector E theta. Okay. Now we'll start discretizing. So how can we write K del T grad T of east dot A east will be nothing but A east PR rho by dou T rho by dou R of east E theta 1 by R of east rho by dou again this is will be of east as well dot del R E theta. So when you dot the components, E theta will be dot with E theta only. E theta dot ER will be 0. So only the contribution of this term will be there. This can be written as KE 1 by RE rho T over rho theta of. And this is nothing but your RP only. Okay. Okay. So if east is this, so how can I write similar manner? K grad T of west dot A west will be nothing but negative of 1 by RE R west dou T by dou theta of. I'm missing some term. Okay, I'm missing this del R. This was missing. Del R. And here as well. Del R. Okay. Now we will see A north. What will be the area of A north? Again, if I make the cell here, this is your north face. So this is how much R del theta, RP del theta. Okay. Into 1 unit. And it is pointing in which direction? ER direction. So A north is nothing but R north you can take instead this time. Because we are dealing with the north face. I should take north. R north. AN will be R naught del theta that is pointing in ER direction. Here it doesn't matter because RP, R west, R east all were equal. But here the radius will matter, R north, R south. Okay. So for again, K grad T of north dot product with A north will be nothing but KN. And it is in R direction, so contribution will come from which term? This time, this term, the first term. So I'll write it like correctly like this. Kn Rn del theta rho T by dou R of north. And what will be for the south? A south minus Ks Rs del theta Dou t by dou r of dou t by dou r of. Okay. So all the grads we have done. Now the point is how we will write dou t by dou theta and dou t by dou r. These terms. Dou t by dou theta and dou t by dou r. Again, you know that linear profile assumptions. So dou t by dou theta of east is t of east minus t of p upon del theta east. In the geometry, we have defined del theta east. And dou t by dou theta of west will be written as t of p minus t of west over dou theta west. Similarly, dou t by dou theta, dou r this time of north will be written as t north dp over del theta north, and dou t by dou r of south will be written as dp minus ds over dou theta south. So dou r south. Here I mistyped. Dou r north, dou r. Okay, I guess no doubts still here. We have described each term. Source term is again linear source term assumptions we have taken. That is SC plus SP. When you will write, again your equation will come like APTP is equal to A east, T east plus A west, T west plus A north, T north plus A south, T south plus B. So where A east was how much? AE del R by R del theta east. Okay. After putting all the values, then I'm only saying this. If you put all these values, your A east will come out to be the coefficient of TE and expand the term, take the TP terms all together. So your A east will be this. Your A west will be K west del R upon RW del theta west. A north will be A north Rn del theta over del Rn, and A south will be Ks Rs del theta over del Rs. And AP is nothing but summation of all the neighboring terms. That is A east plus A west plus A north plus A south minus the source term SP RP del R del theta. Here, this is your B term. Okay. All right. Any doubts still here to anyone? We have discretized in polar coordinates. So the discretization in polar coordinates. Now we will start with discretization using axisymmetric coordinates. Okay. With no doubts, let's come to the next coordinate system. Axis symmetric coordinate system. All right. So here, when we are saying axisymmetric coordinate system, that means the problems which are independent of the direction theta. Okay. The variables t and phi are not dependent on theta direction. So What should I write here? No change of property T or phi along theta direction. Okay. That means if I write dou of dou theta, it will be 0, or dou of dou phi by dou theta, it will be. So our system, that is r theta x system, the r theta z or whatever, will convert to r x and radian system. I'll make the grid, then you will understand. So what kind of problems, axisymmetric problems are there? Like pipe flow on over the rockets, diffusion in a cylinder. All these problems are of axisymmetric. Like pipe flow, flow over rockets, or diffusion in a cylinder, the case which you will deal with. Directly, I'll start with the case of diffusion in a cylinder. Okay. So suppose this is a kind of a cylinder only. So it's an axisymmetric. In the theta, it does not depend. All the values depend only in this direction or in radial r direction or x direction. We have seen plane don't remember Eigenpoisely. So axisymmetric problem. So say that we calculate the velocity r and this directions. All right. So first of all we will create our domain, then discretize it. Because at every direction of theta in the pipe flow, properties will be same, but the properties will change when you move from one point to another point and in this direction. So this is your cylinder. Okay, I'm discretizing the cylinder now. Okay, uniform discretization happen. A uniform distribution of control volumes has made. Suppose my cell of consideration is this. And this is point P. This the upper node will be N, south, east, west, and the faces will be east face, west face, north face, and south face. All right. This length will be del x, and this length will be del r, radius of the pipe or a cylinder, x direction. So this will be how much? Del of x best. And this will be how much? Del of x east. And this will be how much? Del of r north. This will be how much? Del of r south. Okay. So our coordinate system behaves like this. This is r direction. This is x direction. And this is theta direction. So R has a unit vector of ER hat. X is a unit vector of I hat. Okay. Just observe again. Take a minute or two, understand what I've done, and then we'll proceed. Make this diagram with your own hands so that you will be more comfortable. Okay, done. Shall we proceed? Okay, let's proceed then. No, I'll write all the areas here itself. So my east will be how much? If my this is del R, so it will be del R. And what will be my A east? RP, the 1 radian, because it's a you can say cylinder. It's not a Cartesian coordinates. If you observe like this, it has, let me make, so something like curved. It's not straight. So this is your del R. And this will be how much? RP at this point, just a unit cell of cylindrical pipe. That will be RP into 1 radius. Okay. This is your radius till here, RP of the pipe from center. The whole pipe is divided into these small cells. So RP into, sorry, not del RP, del R into RP 1 radian I hat. Similarly, A west will be negative of del R of RP into 1 radian I hat, negative I hat basically. A north will be how much? This is del X. So that is del X into R north. So radius till here is how much? From the center of the pipe, R north, and radius till here is R south. Here all the RP, RE, RW are equal. RN into 1 radian into ER unit, ER hat, and A south negative of LX RS 1 radian ER hat. All the areas are clear? Okay. Because the area is differential, right? Small volumes. The cell looks something like, we make the figure, clear figure again. Suppose if I'm watching the cell from here, okay, this is here, this is here, this is here, here, okay. So this is your R coordinate, this is your X coordinate. So I'm watching from here. Observer is here. All right. So this will be your which face? This will be your north face. This will be your bottom will be your south face. This will be your east face. This will be your east face. Similarly, north, south will be below, and west will be opposite to. And this was your key point action. This is how much? In this direction, it is del R. And this is by this much will be del of theta, independent of theta direction, which is nothing but 1 radian. Okay. All right. Okay. I hope it is, and no doubts are there to know in this kind of figure. Just observe for a second, few seconds. Okay. And what will be the del V of this? Del V will be nothing but RP into 1 radian. Okay. This will be your RP. RP into 1 radian, R theta, this length, this arc length is RP into 1 radian into del X into del R into del X into this is del X RP into 1 radian into del R. This is your volume. How you will write the grad operator? Grad operator will look like E in the radius direction, ER dou by dou R, plus in the I direction, dou by dou X. Our equation is again steady 1D diffusion equation, steady diffusion equation plus source term equal to 0. Again, after applying integrating and applying the Gauss divergence, you will get summation of faces. Those are east, west, north, south. A grad phi grad E dot A F plus linear assumption SC plus SP TP into del V equal to. Now we will discretize this equation. So again, for K grad T can be written for a phase, any phase will be written as K of phase into grad operator is nothing but ER dou by dou R of T of that phase plus E plus I dou T by dou X of that phase. So now we'll write phase by phase. If you want to write, you can write that. Okay. So if I write for the east phase, how it will be K grad T of the east phase will be dot A east also. Dot A east. So A east is we have seen as a contribution of its term, I cap, I hat. So I dot I will be 1. So this term will contribute. So that it will give you AE, RE, del R, dou T by dou X of east. So K grad T of west dot A of west will be how much? K negative of del R dou T by dou X of west. K grad T of north dot A north. This time contribution will come from R term. Okay. So that will be K naught R naught del X dou T by dou R of naught. K grad T of south dot A south be KS RS del X dou T by dou R of south. Now we'll write dou T by dou X and dou T by dou R. Dou T by dou X will be how much? Of east, if I'm writing, that will be T east minus TP. Just I'm writing this one, this term. T east minus TP over del XE. Okay. Similarly, you can write for west, north, south. Okay. Again, and it will be the equation will look like something APTP. You can write for the other terms as well. APTP equal to summation of A and B, T and B plus the term B. The term B. So here A east, A west coefficients will be A east will be after you put all the values AN, RN, del X over del Rn. Okay, A west will be Kw Rw. Why I am writing Kn? Sorry, Ke Ke Re del R over del Xv. Kw Rw del R over del Xw. A naught will be Kn Rn del X del Xn, and A south will be Ks Rs del X over del Xs del Rs. Del R no del R, and AP will be nothing but summation of all the neighboring nodes. A east plus A west plus A north plus A south minus the term B, which is nothing but, or I should write SC, SP, RP, del R, del R. And this is your term. So we have discretized using excess symmetric answering. Any doubts in here? Any doubts? Okay, no doubts. All right. I hope everything is clear till here. Very simple thing. So we have seen all the three type of coordinate system: Cartesian, polar, and axisymmetric for the steady diffusion cases. Now we will come to unsteady diffusion. Okay. Unsteady conduction equations. All right. Okay, so our equation looks like from the initial lectures, if you observe, this was our equation. Del dot rho q phi is equal to del grad of phi plus s. If I make some 0, my boundary condition is like x is equal to xc, y is equal to yc at t. Initial condition. Let me write initial condition first. IC initial condition 5 of t equal to 0. We have x, y, and after some time, phi of x is equal to xc, y is equal to yc at. So this is a parabolic kind of type of equation. We have seen all the kind of equations. And here it's a unsteady equation. Okay. So we have unsteady part, diffusion part, and source part for this equation. So del t is nothing but what is happening from time t to time t plus delta t is happening. That is, when we are doing the integration, we will do two integrations, one over the control volume as well as with time. Let's start doing integration. First integration over time, e to t plus dt plus delta t, and over the control volume, delta v. So dou by dou t of rho phi dv dt is equal to over the control volume, p to t plus delta t, and del v dou by, sorry, del of at phi dv dt plus, again, del t you can write, del v you can write, source term, dv. Okay, this is your integration. First, you will see the dt term, unsteady term. Let us see the unsteady term. So my unsteady term is t to t plus delta t rho by dou t of rho phi dt dv. So I have to integrate. That means it will be rho phi of t plus delta t minus rho phi of t into dv. I assume that for my whole control volume, the value of at a particular t plus delta t or t will be at point P, that is center of the control volume. Okay, so I will write it as rho phi of P at t plus delta t minus rho phi of P of t into linear profile assumptions. Okay, that means this value is our current value, and this value is our previous time value. Okay, current value and previous time value. So I'll denote it as 1, and I'll denote it as 0, and I'll denote it as 1. Okay, I'm denoting it as, not equal to 1. Rest about the other terms. So my other term is this fusion term. How you write? T to t plus delta t del v del of gamma phi dv dt. So again, how you will write this? Linear profile assumptions, summation over all the faces, gamma grad phi of the faces dot a face integral over t to t plus dt delta t into dt. Again, this can be written as t plus delta t and t at t plus delta t and t. What is happening? All right, here linear profile assumption in time. Okay, linear assumption in time. That is nothing but if I make a graph with axis t, so I have a value. So here I have a value. So got phi f. Should write it separately here. Gamma got phi f at 0. That is a time t. Because it's a linear profile assumption. So here the value will be gamma got phi f at 1. Okay. So there is some interpolation factor which is from 0 to 1. Okay. When we are integrating with respect to time. Okay. So how can I write? As of two values at 0 and 1, there is some kind of linear variation between these two values. So we are talking about this direction from here, from 0 to 1. We can use some interpolation factor. Okay. Interpolation factor f. That has value from 0 to 1. So how I can write? F value will have influence for the diffusion term at t plus delta t. That phi f dot ef at 1 plus 1 minus f. Remaining influence will be of at time 0 time t. Okay, time t. All right. This is how you can write with respect to interpolation factor, and this will be whole multiplied. So this is at integral of t to t plus delta t. Linear profile assumption has been assumed. Dt. This is nothing but f phi f at 1 f plus 1 minus f at phi f at 0, and this will be multiplied with delta t. So it's a summation on all the faces time dt. This is nothing but delta t after integration. Okay. So for east phase, how you will write? If I want to write for east phase, gamma at phi at 1 of east phase dot a east will be nothing but gamma east del y. A east will be how much? Del y for this. It's a Cartesian coordinate. This is del y in the east phase. This is del x. The east faces and pointing in the direction del y del x east. This is your point P. This is x east. And phi can be written as phi east minus phi P over 1. Okay, this is your And this is at point 1 t plus delta t. Similarly, if I want to write at 0 at east face itself, dot a east, then it will be again gamma east at 1, gamma east at 0, del y, phi east at 0 minus phi t at 0 over del xc. Okay. You will write like this. Now for the source term, how you will write? Now you have to think how you will write for the source term. Take few seconds and think. Okay. It is right for the source term itself. Our source term was S phi from t to t plus delta t, delta v, S phi dv dt can be written as again linear source SC phi p del v and integral over t to t plus delta t. So again, it will be written like SC plus SP phi p at 1 with a fraction f, linear assumption, plus 1 minus some fraction into SC plus SP phi p at 0 into del v del t. Del v del. Same thing we have done. Yes. Now let us put all the values back into the equation. And similarly, if you have a rho term also, rho phi p of del v minus at 1 and rho phi p of 0 into del v, it will be look like this. Okay, for the rho phi. Yes. Now let us put all the terms and combine together. If you put all these terms and combine together, what will you get? Take a minute and write the terms and let me know. Okay, I guess you might have written. Let's combine all the terms now. See, so f of summation of f phi phase at one of phase plus one minus the factor summation drag phi of 0 of af is g plus f of source term sp phi p of 1 p plus 1 minus f sp plus sp phi p of 0 del v del p. Okay, these are the two terms if you put together. Now, final term will be all the coefficients of phi p will be together. That is rho del v del t plus summation of the nodes a and b minus f sp del v equal to f of summation a and b phi and b plus 1 minus f of summation a and b phi and b naught. Okay, minus 1 minus f of summation a and b phi p naught plus rho del v over del t phi p naught plus vector f of sp plus 1 minus vector f of sp plus sp phi p of naught into del v. This is your AP naught term. Okay. So what can we write now? AP phi p is equal to f of summation of a and b phi and b plus phi p naught AP naught plus 1 minus f sp del v minus 1 minus f summation of a and b plus 1 minus f summation of a and b phi and b naught plus f sp plus 1 minus f sp into del v. Okay, when you will put and rearrange all these terms, okay, you will get your equation like this. We will do further things also, maybe in the next tutorial. Okay, so we did a lot of things today. We started with two-dimensional TDMA problem. Okay, we started with a two-dimensional TDMA problem. Then solved this problem. Then we understood about the under and over relaxation terms. Then that Gauss-Seidel successive over relaxation for nonlinear problems. Alpha is the relaxation coefficients. It will, this is the relaxed equation and at convergence. It only changes the path of the solution. but recovers the original linear system of equation, and it must satisfy this condition after convergence. And then we dealt about the coordinate system. Cartesian we have already dealt in previous tutorials. We dealt with the polar cylindrical coordinates or axisymmetric coordinates. So this was the polar coordinate. Then we came up with the axisymmetric coordinates independent over the theta direction or flow in the pipes. Like then we came to the unsteady conduction equation. That means it is dependent over time as well. So these are the unsteady terms. Discretizations happening for the diffusion term. We assume the linear profile assumption. I consider a factor f for the interpolation. Then for the source term as well, the same thing. Put all the values together. This was the R equation which we got so far. I hope there are no doubts. I think we can end our session. All right. So you guys can leave. Thank you.